So, our speaker for today is Simone Maletto, who will talk about the L function of an elliptic curve over Q.
From the University of Vancouver.
From the University of British Columbia. Yes, thank you. Thank you. It's a pleasure now to be able to talk here for the first time since I left. And today we're going to be talking about the L function of an elliptic curve over Q. And before introducing what is the L function of an elliptic curve, let's talk a little bit of what is an L function in general. So what is an L function? Well, an L function usually is a function of complex variable denoted by L of S of the form sum of an over n to the s for some s in C. And usually this function of this form will have some complex coefficient an and some boundedness of the coefficients will grant the absolute convergence of L on some half plane of the form real part of S smaller than bigger than a positive real number alpha. So those L functions are able to I don't know how to say it, able to contain some surprising arithmetic information. And the first example of this behavior is the most famous L function, which is zeta of S, the Riemann zeta function, which is given by the sum of 1 over n to the s. And I would like to take a moment to use this as a prototype example for interesting and required properties of L functions, which are, first of all, L functions usually are required to have an Euler product form, meaning that where does one see the relation between z of s and the arithmetic of the integers? Well, z of s can be written as the product of 1 over 1 minus p to the s over p prime in z. And now here it's a little bit more clear in this writing why zeros of this function should lead to, in some sense, to talking about distribution of primes. Now, the whole Riemann hypothesis talks about the zeros of these functions over the line with real part equal to 1/2. But it's pretty clear immediately that when we try to look at what is this plane does not include a half. Actually, this expression of z of s converges absolutely to a holomorphic function on real part of s bigger than 1. And how are we able to make sense of this function outside this domain? Well, there is a process that is pretty standard in L function of something you have to do, which is talking about analytic continuation and functional equations. So the idea is we have our zeta function defined over here with a pole at 1, and we would like to talk about what happens on this side of the plane. And to do so, we need to find a formula to define z of s here, which is not going to be this one, of course. And what we do, first of all, to do this, we recall the definition of the gamma function, gamma of s, which is none other than the integral between 0 and infinity of t to the s minus 1 e to the minus t in dt, and then define a function lambda of s to be e to the minus s over 2 gamma of s over 2 zeta of s. And now it's a theorem, somebody can check that gamma s is equal, lambda of s is equal to lambda of 1 minus s. And therefore, we get a functional equation for zeta which is, let's write it this way, p to the minus s over 2, gamma of s over 2, zeta of s equals p to the s minus 1 over 2, gamma of 1 minus, oh my god, gamma equal p to the s minus 1 over 2, gamma of 1 minus s over 2, zeta of 1 minus s. And now the behavior of zeta for real part of s bigger than 1 allows to define something with real part less than 1. And so this method of proof proves a functional equation, which can be either this one, regarded as this one, or this one. But since this functional equation involves stuff that is analytic, okay, it actually provides a way to extend zeta over here. And so if somebody wants to talk about the famous critical strip, which is this sector, one has to prove something along these lines. And if you notice here, 1/2 is exactly the point of symmetry of this equation. So s and 1 minus s. Sorry?
Pi here is pi.
Pi is pi, yeah. I mean, pi shows up in critical values of gamma of s, so it's natural that there are going to be some coefficients of pi showing up. Now, we want to do something along those lines about elliptic curves. So we want to produce an L function of some kind associated to an elliptic curve over Q. And the hope is that this L function encodes arithmetic information on the elliptic curve. Arithmetic information about the arithmetic of the elliptic curve. And so to do so, we have to take a little bit of a journey on what are the types of singularities that an elliptic curve can have. So, well, we take our elliptic curve over Q. Now Q is a field of characteristic 0, so we are allowed to write it like this for a moment, and then we will have to change. And to this one, we associate a quantity called the elliptic discriminant delta of E, which is minus 16 4a cubed plus 27b squared. And now we call another equation of this kind E prime a minimal model for E if E prime is isomorphic to E and the absolute value of this discriminant is minimal.
Isomorphic means higher complex biomorphism.
Rational, I would say.
Rational. Okay. So birational.
No, I mean there is so there is a morphism of elliptic curves that it's defined over Q essentially. So you have to do a little bit more work.
An isogeny?
Yeah, I mean it's an isogeny which is an isomorphism. But yeah, so now I have to erase stuff. Once we get a minimal model, we have to look at the types of reduction that this minimal model has. Meaning, now we have to move, we have to talk about reduction of elliptic curves, so we have to allow characteristic 2 and 3. So from now on, for a little moment, we have to write our elliptic curve in the ugly way. F is equal to y squared plus a1xy plus a3y minus x cubed minus a2x squared minus a4x minus a6. And now let's say P is a singular point of this cubic. Actually, let's assume it's singular, so P is the singular point of the cubic. We take its Taylor expansion, the Taylor expansion of the cubic at P. So we consider F of xy minus sf of xp yp. Okay? And this will be of the form lambda 3, sorry, lambda 1, no, let's keep a step. Lambda 3, y minus, change my mind. Lambda 1, x minus x naught, xp square plus lambda 2, x minus xp, y minus yp, plus lambda 3, y minus yp square plus the term of degree 3. Now, it's important to do the steps separately because now we can see a little bit of what's going on. This rewrites, but not over our field a priori. 0 minus alpha x minus x0 times y minus y0 minus beta x minus x. Those are all p's. P plus x minus xp cubed. Now let's say this expression is with the i's in k, a field.
Just, I'm sorry. Yeah. What do you mean by the singular point of
This cubic, it's a cubic, so it has only one singular point. Because if it has two, you take the line between 2 points, and it will give you 4 points. But it's a cubic, any line intersects in 3 points.
And it always have one singular point?
At most one. In this case, we are taking the case, we are talking about, we are considering the case in which we know it's singular, then it has one. Sorry, thank you for the question. So, in particular, the lambda i's are still in K, but alpha and beta may live in a quadratic extension of K. And sadly, this is relevant for us, so that's why we mention it. We will have to use this in a definition. First of all, we are ready to give some intuition of why, of what can happen. So alpha and beta, if you look at this equation here, as is writing over here, are the slopes of 2 tangent lines at a singular point. And essentially, we have 2 different behaviors, which are called a node, and I'm never able to do this one, a cusp. So this is called a node, and this is called a cusp. And in particular, this allows us to define the type of reduction of E. So E elliptic curve over Z, so we ask if we can make sense of reduction modulo P, has let E, how do we write this sentence? Let E, the type of reduction of E is of E at P is okay, good if E is smooth over FP, additive if E has a cusp over FP, split multiplicative if E has a node over Fp and alpha and beta belong to Fp, non-split multiplicative if he has a node over Fp and alpha and beta are in the only unique extension of degree 2. Okay. Now, I would like to immediately talk about the L function from here, but I need a definition for later, which is the one of an algebraic invariant associated to the type of reduction of elliptic curve. Basically, it's a known fact that a curve is a singular at a prime if its discriminant is divisible by that prime. But what type of singularity do you have? It's encoded in this following algebraic invariant. So we defined an algebra of E, algebraic conductor, and algebra E is equal to the product over the primes dividing the discriminant of E of P to the Fp, where Fp is equal to 1 if E has multiplicative reduction of P, doesn't matter if it's split or not split. 2 if E has additive reduction at P, which is different from 2 and 3, and if P is 2 and 3, one has to add a technical invariant called delta P.
Can you see why it's called split?
Oh, split just because the two tangents split actually, like you have the tangent lines.
From geometric sense.
Yeah, it's a geometric meaning, yeah.
Even if the algebraic connector is there also a geometric?
There is an analytic conductor. There is an analytic conductor which I will not go into.
It's different from.
No, they are the same, and the reason why you need this one is the same. It's because they have. If you want them to agree, you have to define this way with this extra conductor. If you want, we can talk later about what is the analytic conductor of an elliptic curve, but we don't really have time right now because I have to rush through this theory, which is very rich and very beautiful, but we are now to define the L function of an elliptic curve, and then we have to do a lot of work to actually get some result on it. So we to define the L function of elliptic curve, instead of defining a straight up a series, we define an Euler product, and to do so we have to define what is called an Euler factor at P, which is a polynomial LP of T. One can I erase this, but okay. One set LP of T to be equal, no space, LP of T to be equal to 1 never remember set, minus APT plus PT square if E has good reduction at P, 1 minus T if we have split multiplicative, 1 plus T if E has non-split multiplicative, and 1 if additive. And then we are ready to define, I didn't define the P, where AP is the quantity, number of points of the projective curve E over FP, minus, the other way around, number of points of P1 FP minus number of points of E over FP. This is P plus 1. And now we are ready to define what the function is. LEIS is the product of LP evaluated at P over P prime. Now, there is an actual bound on this quantity AP called the Hussey bound. Absolute value of AP is always smaller than 2 to the square root of P. And this allows you to prove that LE of S converges absolutely on real part of S bigger than 2. Now, what we would like to do is to show we have a functional equation for LE of S, and therefore analytic continuation, and we can finally talk about the value of this function at 1. But to do so, we have to do a lot of work and talk about modular force. So, do you want to take a pause now, or should I get into modular force? Okay. Any questions so far?
Why is it P plus 1?
Sorry?
Why is it P plus 1?
It's the point of the number of points of the projective line of a rational field.
Okay, P1 is projective.
Yeah. AP measures the number. You have a projective curve. You can count the discrepancy between the standard projective curve. Okay. So there will be a lot of definitions of modular forms that I will give. I will not give, sadly, a lot of insight because there is too much to talk about, and I just want to do exactly what is necessary and not much more, which is a lot already. So, modular forms. So we start by denoting by H the set of complex number with positive imaginary part.
Can I ask a question?
Yes.
But the Riemann zeta function is associated to some elliptic curve via this process?
No, it's associated to, so if you want, so the correct generalization to look at the Riemann zeta function is what is called, I think, an Artinel function, which is Artinel function, which are L function associated to ring of integers of number fields.
Okay.
And in this scenario, you can see maybe this Riemann zeta function as the one associated to Z.
Okay.
There is some stuff that I don't know about the field with one element. I think people are talking about that to talk about the Riemann zeta function, but it's not my area of expertise. But yeah, no. This is there is essentially like a different dimension going on because L functions of elliptic curves are a higher dimensional object in some sense. Zeta functions are of smaller dimensional objects. Even in terms of representation, like you can talk about the character, the trivial representation of the multiplicative group, and there was the zeta function appears. But to talk about representation here, you always have two-dimensional representation associated to elliptic curves. Okay, so this is H. Let's say hi to H, and we will denote by this object, which is a very strange form of writing, but it's actually just A, B, C, D, such that in M to Z, such that 0. And now we have an action of M2 on H, given by A, B, C, D, and Z, equals to AZ plus B over CZ plus B. And from here, we can do the standard trick of endowing the space of holomorphic function on H with an action. In this case, we will define what is the slash K operator, which is from holomorphic function from H to C times M2 plus in the space of holomorphic functions again, defining F slash k gamma, where k for us will be always be an even integer, is equal to determinant of gamma to the k minus 2, cz plus d to the k, f of gamma z. This is called the weight k slash operator. There is a reason why it's defined this way. We will not go into that way, maybe later as a question. Importantly enough, now we can give the definition of what is a modular form. Definition. A modular form of weight k and level 1 is an holomorphic function on H such that 1 f slash k gamma equals f for all gamma in SL to Z. This is the special linear group of matrices of determinant 1. And the limit, provided goes to infinity, of f of x plus iy exists and it's finite. This is for geometric reasons. So you can see this upper half plane as a disk, the exponential map, and the limit at infinity is talking about the center, what the behaviors of the function at the center of the disk. But again, for this stuff, we can talk later. Now, just a bit of remarks. We denote the space as mk or mk still to z. Is a vector space, is a complex vector space of finite dimension, and while adding together as two forms that respect this condition does not change this condition. If we multiply together, we have to add the weights, and so we can actually form a grid algebra MSL to Z, which is none other than the sum over all weights of MK. And now, to make this make a little bit more sense, let's give the standard example of what is a modular form, which should somewhat resemble a zeta function if you want, but it's a bit.
Wait, I missed a step. What is MKS?
It's the space of those.
Okay.
It's just, this is a vector space, and we just need to give it a name. They're called modular forms, so M. Weight K is okay. So now, we set GK of Z to be the sum for M and N in Z square minus the trivial vector of 1 over M plus N Z to the K. Recall that K is in Z and it's even, so this makes sense. And then one sees that this sum converges to a holomorphic form of array on H, and let's at least see once show the proof that something is modular. So now we take gamma equal to A, B, C, D in SL2, and now we want to compute GK slash gamma K of Z. We look at the definition which is there. Determinant of gamma to the k minus 2 is 1 because gamma is in SL2. Then we have CZ plus D to the K. The sum 1 over M plus N AZ plus B over CZ plus D to the K. This is none other than 1 over CZ plus D to the K, sum of CZ plus D to the K over M times CZ plus D plus N times AZ plus D plus D. Oh, to the K. So this cancels this one. And we are left with sum 1 over, this is very hard, MD plus NB plus NA plus MC. Z to the K. But now this vector, if I'm able, is, we started with N and M. We want an A here, and a C here, and a B here, and a D here. So this is the transpose of the matrix we consider. So but this is the matrix in SL2. So it preserves this lattice, and the image of 0 is given by 0. So this is just acting as a permutation of these indices. Therefore, this is equal to GK of 0. Okay, this makes sense. Those are functions that take weight against the lattice. And in particular, for future use, future means like 5 minutes from now, we would like actually to define special normalization of this guy. So we set EK, the Eisenstein series of weight K, to be GK over twice the zeta function evaluated at K. Why do we do this? Because now, if we look at a little bit of what matrix are in SL2 and what does this action do, the matrix T equal to 1, 1, 1 is in SL2. And if we take a function f in MK, then we have that f slash kt is equal to f. In particular, we get that f of z, which is this f, is equal to determinant of t, 1, over cz plus d to the k, well, c is 0, d is 1, which is again 1. F of t times z is f of z plus 1. So those functions are periodic of period 1. So all elements of MK, which I promptly erased, can be written in a unique way in what is called a Q expansion, sum of an to the n, for some complex coefficient an. And in particular, EK will be equal to 1 plus sum of stuff. This is why we take this normalization. And why do I go to the bother of doing this? Because we have another important definition, now that we know what is a Q expansion, of a special subset of MK. So, definition, a modular form is a cusp form if A0 of f is equal to 0. So modular forms whose first Fourier coefficient, Fourier coefficient is 0 is called cusp forms.
I haven't understood what's that Q form.
Q is
because period 1.
yes, so you can take
Why?
you define Q to be e to the 2 pi iz. Okay.
Okay, it's just period that's Fourier.
It's a Fourier expansion. Yeah. They are Just
Okay, I missed the part in which you find.
No, yeah, I didn't define Q, sorry. I just said they have a Fourier expansion. Yeah, it's not a honest to God Fourier expansion. Okay, in particular, we can now make an example of an element, the space of those is denoted by Sk, in this case of SL2C. And now the first example of an element in Sk is what is called the modular discriminant delta, which is related to the J invariant, which I think you talked about last time, which is now given by something fairly annoying on the coefficient. So it's on the other page. Because there is always this 2 pi to the 12 that I forget. The part that I should remember is E4 cube minus E6 square over 170. And now, since we normalized EK this way, so that starts with a 1, it's pretty clear that the first Fourier coefficient of E4 cube is going to be 1. The first Fourier coefficient of E6 cube is going to be square is going to be 1. We subtracted. This is first Fourier coefficient 0. This is our first example of a cusp form. And now, to understand why those are relevant, we're going to work a little bit more, but we can do this after the break. Welcome back. Since we had a little pause, I kept these important definitions, and it's a good time. It's like it seems appropriate to start with a definition that is an extension, but also a recall of what is a modular form. In this case, not more of level 1, but now of level gamma naught n. So definition: modular form of weight k and level gamma naught n is an holomorphic function on H such that there is still the limit condition for y equals to infinity of f of x plus iy exists finite, but now we have that f slash k gamma is equal to f for gamma in gamma naught n, which is what? Let's make a line break. Gamma naught n is a subgroup of SL2Z. It's an example of what is called a congruent subgroup. In this case, are the matrix A, B, C, D, such that in SL2, such that they assume this form modulo n. So it's the pre-image of the upper triangulars of Z mod and Z. So these three numbers can be whatever they want, provided the determinant is 1. And the bottom low entry is equal to 0. Okay, and we denote the space with nk gamma naught n. It will contain a space of cusp form since 1, 1, 1 is still in here. This makes still sense. This is denoted by sk gamma naught n. It's still a vector space. It's still a graded algebra. We all have these amazing properties. And now on this space, we put on some extra structure. In particular, we define an inner product. So, definition. This is called the Peterson, and I hope I don't misspell it, but it should be with 1 T and 2 S in the product. F between F and G. Let's write here N, which is none other than the integral over Bn. Now give me a second. F of x plus iy G conjugate of x plus y, y to the k minus 2, dx dy. Now, Bn is a fundamental domain for the action of the subgroup gamma naught n acting on H. So a little bit of comments. This product is positive, definite, and defined in Hermitian form on the space Sk. This kind of integral doesn't actually require both the elements to be in Sk to converge. It only requires one of them to be in Sk. But to ensure convergence and having actually a bilinear form, we need to put our Sk, because on an element of Mk and Mk, this doesn't work. Now that we have this beautiful inner product, we define some infinite family of commuting operator on Sk, and these operators are actually of utmost arithmetic importance, and I'm going to do a disservice and give the most basic form of definition, because else we're going to stay here for like 3 hours to talk properly about them. So let us introduce Hecke operators for gamma naught n. And we start by choosing a prime P prime and F, a cusp form of weight K and level gamma naught n. And let's say that the expansion of F is sum of an q to the n. This is a writing Fourier series. Then we define an operator Tp as, Tp of F as sum of A and P q to the n if P divides n, and sum of A and P q to the n plus the sum of A n q to the np if P does not divide n. Just to mention, usually in this case, I'll actually talk about the operator up instead of tp. Some people just use tp. Depends on conventions. But from here, we can now define the operator tp to the r to be tp to the r minus tp to the r minus 1 minus p to the k tp to the r minus 2, and tn to be the product over e to the ei dividing exactly n. Everybody comfortable dividing exactly as a symbol? Makes sense? Divides exactly, meaning the quotient p to the I divides n, and the quotient is not divisible by p of t p to the I. Now with this bunch of definitions, we create a family Pn of operators such that Tn Tm is equal to Tm Tn if Mn are coprime. In particular, if we take, the family of the TPs, the variable primes, is made of only coprime indexes, and therefore all of them commute. Furthermore, in this case, so if P does not divide n, TP is self-adjoint under vectors of product. And for completion, and as an excuse to introduce this thing, if P divides N, the adjoint of TP tag, is going to be Wn TP Wn inverse, where Wn is defined as the slash k operator with -1 with this matrix, which is called the free k or arc linear involution of level n, and it's Mickey Mouse meme. It's gonna be useful later. So now what we have is a finite dimensional vector space with an inner product and a commutative family of self-adjoint operator, an infinite commutative family of self-adjoint operators. So we can use the complex spectral theorem, and we know that it exists a basis of Sk gamma naught n composed of simultaneous eigenfunctions for all the Hecke operators Tn, and for now what we have actually proved is this is only true where n is coprime with the level. With some extra work that we will not do today, we can remove this hypothesis. We can actually prove that the system of eigenvalues identifies uniquely a one-dimensional eigenspace. It's called strong multiplicity 1. But now that we have all of these, we can talk about eigenfunctions. So, definition, an f in Sk gamma naught n is called an eigenform, let's say normalized eigenform, a normalized eigenform, oh my god, eigenform if this way non è abbastanza asciutto. Let's spray. No. Later, if how such a struggle. If f is a simultaneous eigenvalue for all Tn, the first Fourier coefficient of f is actually equal to 1. And actually, one can prove from this a little bit of magic that if we write lambda n f to be the eigenvalue of f, we have that lambda of n is actually the nth Fourier coefficient. Okay, where are we? Yes. Okay, last leg before talking about L functions, we have to talk about new forms. So we have these spaces of modular forms of various levels, but you see when we define gamma naught n, the levels are kind of like linked to each other because this n has some divisors, and there is a relationship between forms of lower level and forms of higher level. So what I'm trying to say, if now D divides N, we have two maps, Sk gamma naught N over D, Sk gamma naught N, which are very simple. The first one is f of z maps to f of z, and the second one is f of z maps to f of dz. Those maps are actually equivariant respect the Hecke operators away from n, meaning coprime with n. And we can glue them all together to get, in some sense, a notion of what modular forms are new at n and what modular forms come from some level lower than n. So we can define a map I, sum for d dividing n of sk to the n over d squared into sk, sorry, gamma naught n. So now we have this inclusion, and we did define in the product. So this, using this map, we can construct two spaces, sk old, which is going to be the image of I, and sk new, the orthogonal complement to sk old. And we will focus on this guy. Last definition regarding exactly only modular forms. A normalized eigenform is called a new form if it belongs to the new piece of SK. Okay, this is what we need now to go back and talk about the L function of a modular form. So what is the L function of the modular form? Well, the first definition is actually pretty straightforward. We have a modular form F. This has a Fourier expansion. The modular form a cusp form, technically. And from this we can just form an L series. And it is called LFS. Now, why did we go through all of these? Well, let's look at the function a little bit more. First of all, one can show that if f is in SK, gamma naught n, then LFS converges absolutely to a function on the half plane with real part of S bigger than k over 2 plus 1. And we have an Euler product factorization LFS equal to the product 1 over 1 plus 8p p to the minus s plus 1n of p p to the k minus 1 minus 2s, where what 1n of p is 0 if p divides n, 1 if p does not divide n. Now let's look here. Okay, and let's look here, or for the people online, rewind to when we find the localized factor of an elliptic curve. I don't know if you can see it. So there is some striking resemblance. If we set k equal to 2, real part of s bigger than 2, which was true for a function of an elliptic curve, and this p becomes p to the 2 minus 1, so p to the 1 minus 2s, which looks like this guy, so that's fine. But that this guy has this character here, 1 of n, that can kill it, but we should be fine about killing this, because this is encompassed on some multiplicative reduction cases. So the idea is, maybe this L function is linked to that one. And it's going to be the end of our talk in some sense. But before, remember that the function of elliptic curve, we didn't do all the job. We showed some other factorization, but we weren't able to say anything about analytic continuation or functional equations. And this stuff, in the case of modular form, comes actually for pretty much for free, meaning that we have to introduce a couple objects, but then it's rather easy. I'm sorry, this will register poorly on camera, but the water experiment did not pay off. So let now f in sk gamma naught n be a normalized eigenform, and let's define the Mellin transform of f, g, the integral from 0 to infinity of f of it, t to the s minus 1 in dt. Then, first of all, whenever s is such that the g, this integral is well defined and convergent, we immediately have the g of s is equal to 2 to the pi to the minus s gamma of s, the L function of f evaluated of s. Furthermore, g of s does fit in a functional equation. We write lambda n of s to be n to the s over 2 g of s, and then we have lambda n of s is equal to omega times lambda n k minus s, where omega is the eigenvalue of f under the involution Wn that we define. If being an involution, it means that this eigenvalue can be only plus or minus 1. So this is going to be plus or minus 1. But in particular, now we have a functional equation, an analytic continuation of LFS. So we have done the work for modular forms. In the case of way 2, actually, we see that this is 2 to the minus s, and so we expect some symmetry, some critical state, critical information at 1. And now let's state a theorem that we have all heard about it very much, but couldn't state in any form before. Theorem. Modularity. Version L. Let E be a rational elliptic curve of conductor NE, then there exists a new form F in SK gamma naught NE such that L E S equals L L S. And well, this is pretty exciting on itself, but also if you spend a second to think what is written here and what is written there, this AP have sensibly different meaning in the two. So this coefficient AP and modular factor was a Fourier coefficient of a form of a function of complex variable, and this AP over here was a natural number associated to a difference of points on curves. And saying that these two functions are the same is implying that those two are equal. And furthermore, as a consequence, we had all this magical property for this function of having a functional equation and analytic continuation, and now for free meaning Taylor-Wiles, we have them for ES. So now we can do what we hope to do and investigate the property of LES and the critical strip, which is going to be now S equal to 1. This is not SK, this is S2. Those are always with. Okay, to state the conjecture at the end of this talk, let us give a recall. I think last time we talked about elliptic curve, it was mentioned what is the Mordevai theorem in particular. Let me recall. The set of rational points of elliptic curve is a finitely generated abelian group. So it's isomorphic to T plus a free group Z. And let's call this R algebraic rank. Now let's make a definition. Let R analytic rank be the order of vanishing of LES of B, of course, at S equal 1. So the last thing we want to say is the following. Conjecture coming from, I believe, the 16th at Cambridge, Birch, Swinnerton-Dyer in weak form. The analytic rank of the elliptic curve is exactly equal to algebraic rank, which is still a millennium problem. Okay, this is all I wanted to say, which was quite the marathon. I'm very sorry about that. If anybody has questions, please let me know.
Thank you, Simone. Is there any questions or comments?
Swear words I'll take.
Okay, that does not seem to be the case, so let's thank Simone again. And resume next week. Thank you.